Welcome to this tutorial on solving second-order linear homogeneous differential equations. Today, we'll solve the example equation y double prime minus 4, y prime plus 3, y equals 0. We'll solve this using the characteristic equation method, which works for linear homogeneous differential equations with constant coefficients. Here's our approach. First, we'll form the characteristic equation. Then, we'll solve for its roots. Finally, we'll use these roots to write the general solution. Let's start with step 1, forming the characteristic equation. We assume a solution of the form y equals e to the power of our x, where r is a constant we need to determine. If y equals e to the rx, then the first derivative y prime equals r times e to the rx, and the second derivative y double prime equals r squared times e to the rx. Now, we substitute these expressions into our original differential equation. We get r squared times e to the rx minus 4 times r times e to the rx plus 3 times e to the rx equals 0. We can factor out e to the rx from all terms to get e to the rx times the quantity r squared minus 4, r plus 3 equals 0. Since e to the rx is never 0, we have the characteristic equation r squared minus 4, r plus 3 equals 0. Now for step 2, solving the characteristic equation. We need to factor the quadratic expression r squared minus 4, r plus 3. This factors as the product of r minus 1 and r minus 3. Setting each factor equal to 0, we get r equals 1 or r equals 3. So our characteristic equation has two distinct real roots, r1 equals 1 and r2 equals 3. For step 3, we write the general solution using our roots. For a second-order linear homogeneous differential equation with distinct real roots r1 and r2, the general solution has the form y equals c1 times e to the r1x plus c2 times e to the r2x, where c1 and c2 are arbitrary constants. Substituting our roots, r1 equals 1 and r2 equals 3, we get the general solution. Y of x equals c1 times e to the x plus c2 times e to the 3x. Let's visualize some specific solutions from this family. Let's analyze the solution behavior. The term e to the x grows exponentially, but the term e to the 3x grows much faster. As x increases, the e to the 3x term will dominate, causing most solutions to grow very rapidly. We can verify our solution by substituting it back into the original differential equation. Since both e to the x and e to the 3x are linearly independent solutions to the differential equation, any linear combination is also a solution. In summary, we've solved the second-order differential equation y double prime minus 4, y prime plus 3, y equals 0 using the characteristic equation method. We formed the characteristic equation r squared minus 4, r plus 3 equals 0, found its roots r1 equals 1, and r2 equals 3, and wrote the general solution y of x equals c1 times e to the x plus c2 times e to the 3x. This approach works for any linear homogeneous differential equation with constant coefficients, though the details of the solution form will depend on the nature of the roots. Thank you for watching this tutorial on solving second-order differential equations. The characteristic equation method is a powerful technique that will help you solve many differential equations you'll encounter in your studies.